we went through this and we sort of figured this whole piece out. And so the part of this moving on is taking the same basic idea, what we have in this table, which is to, to write the value down, indicate its frequency and stuff. But we can do the same thing sort of visually, graphically. So with 50, we can put all the, let's see, all the values down here. So 57, let's make sure I don't skip any this time. 60, 61, let's see, 62, 63, I think the rest of it should go pretty much the rest of the way. 64, 65, 66, 67, that's a horrible 67, you can't see really. 67, 68, 69, 70, 71, 72, 73. Okay, so there's all the different values, and we can actually plot them. Like for 57, there's just 1, so we can actually just have just one bar there. For 60, there are 2. So we can actually see that bar there for 62. For 61, there are also 2. Just keep it going at 2. All right, and then 62, also 2. Okay. You get the idea. This is sort of like turning into what looks somewhat like a histogram, except you'll see in a second the difference is for this is an ungrouped distribution for histograms or for group data. For 63, there are 4. So I'm going to go up here to 4. Oop, wrong one. Here to 4. Down there, all the way down there. Fit all that in. So there's 63, has 4 of them. 64, there are 5. I'm going to go up another one. Okay. And basically just fill in this graph. This marker might be dying. 65, there are 4. It comes back down here. 66, 4. Use a different marker. 67, there are 3. 68, also 3. Okay, I mean, this seems sort of tedious. I'm just sort of making a point. This is like basically how these kind of graphs get put together. And obviously there are programs like SPSS and stuff that will do it for you, or even there's only 169, Excel and stuff. But this is, the basic idea of what's being displayed in each one of these components here. 71, there are 5. I'm sorry, so skip 70. 69, there's 1. 70, there's also only 1. 71, there are 5. Oop, I keep doing that. It's sometimes hard, it's like sort of hard to see. So there are 5, which is here, all the way down to there, and here. Alright, so there's our 70, 72, there are 2. 73, there are 4. All right. So normally I would have done that sort of all in the same color. I only switched because the marker seemed like it was dying. But what do you notice about this stuff? What is this? So first off, compared to the previous the previous version of this, where it was just written out as a frequency distribution table, doesn't seem quite as appealing than having sort of cool colored bars telling you the same information. And this, you know, goes along with this idea that people don't really like numbers. They rather see sort of pretty, you know, bars and patterns and stuff on a graph like this than to actually look at the numbers themselves. But one of the things that doing it this way, graphing it this way, can do is to start looking for patterns that may not be so apparent when looking at a frequency distribution table with all the numbers. So what do you notice about the pattern here of these dots? Again, forget the colors. Just look at the sort of patterns of the bars. What do you notice? Right, good. Use of the word bimodal. I love it. So there's two relatively equal high points, right? So it looks like this is at least a bimodal distribution. Now, do you remember what it is we're graphing? Like, what are these numbers referring to? What was the data set from? Let's go back a couple slides. This was here. Their heights. So this is spring 2018. Students reported their height in inches. So, you know, we are basically graphing that out. So what do you think these two modes represent? Why would something like height be bimodal? Because we have a sort of a cluster of heights that are around this lower mode, around 64 inches, and another cluster of heights that's around this other about 71 inches. Why do we have two clusters? Now, it's likely there are males in here and there are females in here, but what this does, there may be some, you know, taller females, but it does represent that oftentimes we have bimodal distributions, because what we're really seeing is a mixture, a blending of two different subpopulations, one of sort of females and one of males, which is why we're seeing two different sort of central tendencies, one, you know, around the sort of female heights and one around the male heights. So oftentimes when you see bimodal distributions, instead of just thinking about it as, oh, there's just two modes, it's likely what's going on is you have one distribution that's mixed in with another distribution that's causing there to be the two modes. So in this case, we have sort of females on the lower side, likely, and males on the upper side, which is actually causing it. Now there is overlap between them, so it's not like they're perfectly separable, but we are getting these sort of blended distributions, which is causing there to be two different modes. That won't always be the case, but in this case, it does seem to be fairly obvious based on the heights. That's likely what's going on. Questions about this? This is a ungrouped frequency distribution table. Basically, just turning that frequency distribution table this is ungrouped frequency distribution graph or chart, which is based on an ungrouped frequency distribution table. But this is a lot more interesting to look at than the previous table was. All right, so I'm going to erase this. Any questions about this? Most graphs and sort of graphic displays, again, come down to this basic idea that the general population would rather see sort of patterns and stuff like this than to look at a bunch of numbers. I don't mean that in a derogatory way or in a negative way. It's just that numbers sometimes are difficult really to pick up on patterns. It's really, really difficult to pick up on things when they're just laid out as numbers. But if we put them into a graph like this, you start to see sort of patterns. Like you picked up on the fact that there's likely males and females, and their heights are being reflected by the two different modes. So that kind of stuff is cool. So anytime we can use graphs to help get insights into the right data, that's a huge positive. Right? And that's a lot of reasons why we tend to like to graph things and put things into displays like that. Try to get better understanding of our data. All right, moving on. So with large data set. So, I mean, our data set's pretty small, right? It's not a whole lot of data. We're talking about, I think, 34 or 43, I think 43 different responses, right? So it's not a lot. It's pretty easy to graph, to put into a table like this. It's pretty easy to graph each individual score without any issue. When data sets get larger and the data are continuous, meaning that we're not talking about categorical things, so I'm sort of continuous values, it's recommended that you only use between 10 and 20 classes, meaning that when you're looking at bars or the values like this, you don't want any more than 20 of them, because when trying to display them out here, you're going to get these very skinny little bars beyond 20, and it starts to become sort of not super helpful when you have that many categories sort of displaying data. So we want to try and stick to somewhere between 10 and 20 groups or classes of data. So we've got to figure out a way to break that down. So if we want to take something like this data, again, imagine this is not just 43, but imagine it's 430 cases or some large amount. And we want to break it down into smaller chunks to make it easier to sort of to interpret or see patterns. We might want to treat them as sort of grouped distributions, where instead of grouping each and every individual score, we're going to create sort of classes or intervals and group and put them into categories and make them into bars in a graph. So, for instance, one way to sort of choose the number of classes is this sort of class size. I is to take, what's the number of intervals or classes that you might want. So again, somewhere between 10 and 20. I'm going to go with 10 just because it's a fairly small number of scores. Not like we have hundreds. So let's go with the smaller amount. So if we choose 10 as our number, take the highest value, 73. Subtract the lowest number, which is 57. This, by the way, is, this component here is the range, which we'll come back to in a second. Okay. Take the range of the data and divide it by the number of intervals we want. In this case, we're going to use 10. I'm going to divide it by 10 intervals, and that'll give us the size of our interval that we want. So let's do that quick. 73 minus 57. 73 minus 57 is 16. All right, so it ends up being 16 divided by 10, which gives us 1.6. Now, we don't tend to want interval sizes that are decimals, right? So I'm gonna basically round this up to 2. We're gonna choose an interval size of 2. So if we look back at the data, if we start with 57 as our lowest number, we can start thinking about, okay, what does that mean? I mean, they're going to have one interval, my first interval, like interval 1, is going to be 57 to 58. All right, so those two numbers are in that first interval, because I just want 2 numbers in there. Okay, so then interval 2 is going to be 59 and 60. And then we can keep doing that. Interval 3 is going to be 61 and 62. Right? So we're going to start sort of to figure out what these class sizes, right? So we figured the class size is 2. All right, so what numbers go into each of these classes? We start with the lowest number, sort of work our way up. We can just group everything into groups of 2, and those are going to be our classes for our grouped distribution. Now this may seem silly because we only have 43 numbers, but again, you got to imagine doing this for stuff that's much bigger, where we may end up having a bigger range, so having a bigger class size, and we're trying to cut a whole lot of numbers down into just a few classes to graph, to make graphs like histograms and things a little bit easier to interpret. Because with too many bars, it just looks like a bunch of craziness, just random noise. All right, so once we have, so we want class intervals of 2, so we can start thinking about how to make this work. All right, so I have apparent limits, real limits. I'll talk about that in a second. The apparent limits for the first one, again, we start off at 57. My first interval is going to be 57 to 58, and then 59 to 60, 61, 62, 69 to 70, 71 to 72, and down here we got 73 to 74. All right, so now we've made a bunch of classes. Oh, we can go down here now. Instead of looking at the frequency of each individual score, we can look at the frequency of that interval. So I'm going to skip these two columns for a second and come back to them. So look at the frequencies, and it's going back doing the same thing we did a second ago, but instead we're doing it for each interval instead of for each individual score. So how many 57s and 58s do we have? All right, well, we only have one 57, no 58s. So 59 and 60, well, there are two 60s, no 59s. 61, 62, so there's two 61s, two 62s, so that's 4. 63, 64, there are, 63, so there are 4 63s and 5 64s, looks like, so there's 9 there. 65, 66, 65, there are 4 of them, 4 66s, so there's 8 of these. 67, 68, looks like 3 and 3. There's 6 of those. 69, 70. There's only 2. There's 169 and 170. 71, 72. There are 5 71s and 2 72s. So that's 7 of those. 7 of those. And 63, 64 is just 4 63s. So that's it. Okay, so we start talking about the relative frequency. Again, I think there are 43 numbers. So we start looking at 1 divided by 43 equals 0.023. So let's say this is about 2.3%. For 2 divided by 43 equals about 4.7%. 4 divided by 43, 9.3%. 9 divided by 43 is 20.9%. 8 divided by 43 is 18.6. 6 divided by 43 is 13.9, actually really about 14.0%. 2 has 4.7. 7 divided by 43 equals 16.3%. And then 4 is 9.3. Okay. You can start doing the, again, same as last time, same kinds of things, cumulative frequency. So the first one is 1. 1 plus 2 is now 3. 3 plus 4 is 7. 7 plus 9 is 16. 16 plus 8 is 24. 24 plus 6 is 30. 30 plus 2 is 32. 32 plus 7 is 39. 39 plus 4 is 43. And then we start doing the same kinds of things. All right, we can look at the cumulative relative frequency. Well, the relative frequency, again, is like percentage. All right, so this, I really have it to, not to confuse things a little bit, but so I have it as relative frequency, and I've basically taken it to relative percentage because I took the frequency over total but then I multiplied by 100 to make it a percentage. So if I really wanted to make it just relative frequency, this really should be 0.023, and I should have just left it at that. But I actually made it into a percentage just because that seems more natural than leaving it as a decimal place number. But so with this, we can do the same thing where, because this is the first category, it's basically going to remain unchanged. 2.3 plus 4.7, all right, the 0.3 and the 0.7 make a 1. 6, that's 7.0, I think. All right, 3 plus 7 is 1, 2 plus 4 is 6, and 1 is 7. Okay, 7 plus 9.3 is going to be 16.3%, I think. If I do one of these wrong, let me know. 16.3 plus, okay, so 9 plus 3 is going to make this into a 2. 16 is going to be 36, 37, I think. 7.2 plus 18.6, so okay, so 6 plus 2 is going to be 8. 37, all right, so 8 plus 7 is going to make that 45. All right, 45. Just want to make that. Alright, so I can 8 plus 7, it's going to be 15. Makes that 45, 55. I did it right. 55.8. That plus 14 is going to be another, so that's going to be 69.8%. 9.8 plus 4.7, so 8 and 7, again, is going to be 5. 9 plus 4 is going to make that 73, 74.5. Yeah. So Cumulative is asking, like, so if I'm looking at the number, say, in this 65 to 66 interval, right, there's 8 of them. And that's just the frequency of that thing. But what if I want to know how many scores do I have? There's 65, 66, or less. The cumulative sort of frequency that builds up from that number to this point. So to do that, I can either take and add up all these, like 1, 3, plus that is 7, plus that is 16, plus that's 24, to find 24, right? That's the number that is either this category or less, is 24. But because we're doing it one at a time, I just said, all right, so the first category, there's nothing less than that, so it's going to remain the same, right? So this is going to be 1, it's going to be 1 there too. So if I want to add up, well, okay, for the next category, 50 to 59 and 60 category, there's 2 there, and there's 1 in the category before it. So I'm just taking this plus the next 2, give me 3. And this 3 plus the next 4 give me 7. This 7 plus the next 9 give me 16. 16 plus the next 8 give me 24. So that's how I got, there's 24 scores. It's not the distance, it's just, it's asking, it's just how many, instead of asking how many people are in this category, the cumulative is asking how many people are in this category or less. So it's you know, starting from whatever your lowest number is, adding up to that category. So for each category, it's going to be that category and whatever category is less than it. So for this one, it's this category plus that category plus that category. For the one down here, it's going to be this category plus this one plus that one plus that one, you know, all the way back to nothing, which is why it ends up covering everybody, because this is the highest category. Everyone is in this category or less. So when you're talking about cumulative, like in a technical sense, like if you look at a distribution like this, the cumulative like percentage of this is, if this is like negative infinity on this end, it's talking about everything from this side going forward is the cumulative percentage of this. So if I'm looking at a number here, the cumulative percentage is everything to the left. Everything less than that number is the cumulative part of the distribution. right? Not this part. This part is not cumulative. It's everything from the lowest part all the way up to the point you're looking for. It's the cumulative part of distribution. If you're on a negative number on this side here, it's still the negative infinity up to that point. So this is going to be the cumulative part, right? So it's always everything sort of from the lowest value up to the number you're looking for. So that's why the way I found it, I may have done that sort of quick without explaining why, was, you know, if the first category only has 1 in it, I'm just going to transfer it over. There's nothing less than that. There's nothing cumulative up to this point because there's nothing less than that. But for the next one, because there's 2 here, I need to take that 2, but then also add in the 1 from the previous category, which is why it's 3. I need to take this 4, add in the 2 and the 1 from the previous category to give me 7. The 9 plus the 4 plus the 3 plus the 1 gives me 16. Right? So I'm just taking each value and adding what's before it. I just did it in a, to me, what seems like an easier way if I just do it one at a time. So 1 plus 2 is 3, 3 plus 4 is 7, 7 plus 8 is 16, 16 plus 8 is 24, 24 plus 6 is 30, 30 plus 2 is 32, 32 plus 7 is 39, and then 39 plus 4 is 43. I just did it sort of one at a time, so I have each of their cumulative distributions or cumulative frequencies instead of having to do it all at once, like to look at, you know, for this class and add everything up. I was already sort of working my way towards it. And then it's the same thing for the cumulative relative frequency, like the percentage, the proportions. I'm just doing the same thing. So the first class, it's 2.3, so that's just copied over. And then 2.3 plus 4.7 is 7. 7 plus 9.3 is 16.3. 16 point, you know, just sort of adding them together. Hopefully I'm doing it correctly the whole time. When you stopped me, I thought you were going to tell me that I screwed this up somehow. 55.8 plus, okay, so then down here, 74.5 plus the next one. 5 plus 3, this is going to be 8. Like that. And 74 plus 6 is going to give me a 0 there. 7 plus 1 is 8. It's going to go to 9. And then 90.8 plus 9.3 is going to give me, this is going to give me 1. So it's going to be like 100.1. 90 plus another one, yeah, so it's 100.1 is what I get. That's because of the rounding. We're rounding to 1 decimal. It's going to be off a little bit. Questions so far? These are both percentages as well. I'm talking about this column here. So the relative frequency, the first one. No, the relative one. This one. So in reality, I think for some reason I wasn't consistent. If I look back here for a second. Yeah, so in this one I wrote percent and then cumulative percent. And then here I wrote relative frequency, when realistically what I did here is actually not the relative frequency but the percent. Right? I actually wrote out the percent instead of, I just did it, I think, just automatically. It just makes more sense to work with percents than it is to work with the relative frequency. But if I wanted to write this out as written, well, this is the relative frequency instead of the percentage, it's just the same process. I'm just not multiplying by 100. So I keep it as a proportion instead of bringing it out to a percentage. So let's see. So if I were to take I have 1 in the first category. So the total number I have is, there's 43. Well, I'm just going to say n equals 43. That's what we're going to be using later on anyway, is this idea of n. So I have 43 different responses. So how many of those 43 is in this category? Well, there's 1 of them. So as it says in the relative frequency, I'm going to take the frequency, f, divided by total. Okay, well, 43 is my total. So 1 divided by 43, if I leave it alone, I get 0.023 without multiplying by 100. 0.023 is my value. All right, so that technically is my relative frequency. If I multiply that number by 100, then I'm getting the percentage, or the percent that is in that first class. So for 2, for the second category here, there's a frequency of 2. So I just did 2 divided by total, which is 43. I'm getting this 0.047. 0.047 is my relative frequency. Do the same thing for 4. Getting 0.093. For 9, 0.209. For 8, 0.186. 6 divided by 43 is third. I guess I get 0.1395. This means technically this rounds to 0.140. And then 2, I already did that, it's 0.047. 4 I did just 0.0093. And then 7 divided by 43 equals 6.163. So this is a little bit more accurate in terms of how it's written as relative frequency. Is really just asking what is the frequency relative to total, which is another way of saying what's the proportion of the total that is in this category or in the next category, or whatever category you're talking about. Which means that the cumulative relative frequency that's over here, we can do that the same way. Make it, not use it as a percentage, use it as a proportion as well. And just add those numbers up. So 0.023, 0.047, you get 3 and 7. And it makes it into 0 there, as an extra 1 there. So that's 3 and 4, so that's 0.070. Oh, I'm sorry, yeah, here. So this is going to remain 0.023 because there's nothing below it. That plus this, so 3 and 7 makes 10. 4 and 2 makes 6, 7, so this is 0.070. 0.070 plus 0.093, you get a 3. 7 plus 9 is 6, and then a 1, so 0.163, I think. Yeah. 0.163 plus 209, 3 plus 9 makes this 2. 16 and 20 make that 36, so it ends up being 37 because of the extra 1. 0.372 and 0.186. 2 and 6 is 8. 7 and 8 is 15. 3 and 1 is 4, plus the extra 1 is 5. 0.558. 558 plus 0.140 makes this 8. 4 and 5 is 9. 5 and 1 is 6. 0.698. 0.698 plus 0.047. This is 8 and 7 again is 15. So 9 and 4 is, alright, so 9 and 4 is 13 plus 1, then it gives 14. 6 plus 0, so that ends up being 7.745. That plus 0.163, so 5 and 3 is 8. 4 and 6 is 10. 7 and 1 is 8. So makes that 9.908. And 0.908, so 8 and 3 ends up being 1. So it makes that 9, makes that 10. And makes that 10 to 100.1. And so again, it's a little off because, actually not 100.1, 0.1001. It's essentially, no, sorry, 1.001, So we added up all those proportions. We're now getting a number that's slightly above 1 because we rounded everything in the third decimal, so it's going to be a little bit off. But that help? Hopefully makes sense. All right, so that being said, I'm going to do a goofy thing here, which is I'm going to take a picture of this because on the next page that's going to be helpful. All right, so you can look at that. So this is what's called a grouped frequency distribution. So the difference back here, we did an ungrouped frequency distribution table in which we did every single value and their frequencies. Here we made groups, classes, right? We made classes of numbers in which we grouped every two digits together, 57, 58, 59, 60. We made these classes. Oh, I forgot. Let's talk about, before I almost erased. Let's talk about this apparent and real limit and midpoint thing that's on here as well. So if the limits, the apparent limits are 57 and 58. What does it mean by the real limits? What are the real limits as opposed to the apparent limits? So let's say you want to put numbers. If we want to pretend like these are baskets, right? So think of each one of these things as being a little basket that we want to put these numbers into, right? So this is the 63 to 64 basket, the 65 to 66 basket. So these classes are just 2. So it's sort of like we're making a basket, right? That we're saying this is the 50, 57 to 58 basket. So any 57 or 58 gets put in here, right? Okay. The problem is you got to think wider numbers. Let's say we had bigger classes. We had a class that was like, 5 to 10. Okay. What starts to get confusing about this is what numbers actually belong or don't belong into classes. So when you have a class that's defined this way as 5 to 10, it becomes difficult. And the next class then is here, right? When a number comes here, you want to know, should I put it in this class or in this class? It sometimes can be tricky to figure out depending on how the classes are described. They're labeled. So how this works with the real versus apparent limits, if I want 57s, right, and 58s to go in the basket, to go here in the basket, and to differentiate that between the next basket, the limits of this basket really aren't 57 and 58 because I want those to go in the basket, and I want these limits to separate out this basket from the next basket, right? This class from the next class. So what that means is that the limits oftentimes are defined as sort of 1/2 the units that you're measuring this in. These are changing in single units, 7, 8, 9, 10, 11, 12, just in single units. So this is going to be 56.5 is the real lower limit, and 58.5 on the top. So I can now say anything between 56.5, 58.5 go in here. All right, so that includes 57s and 58s. But if I get something that's above 58, even 58.56 is going to go into the next basket. And that's where we're going to make that split between the baskets, is at this real limit. This is the real limit here. This is the real limit there. So that means for this one, I'm going to go 1/2 a unit down and 1/2 up. So the real limits here are 56.5 to 58.5, which means down here, the next real limit should share this. That's the other part of this too, is that the real limits should actually overlap. So here, this is going to be 58.5 to 60.5 are the real limits here. Next one's going to be 60.5 to 62.5. And 62.5 to 64.5. 64.5 to 66.5. 66.5 to 68.5, 69 point, nope, 68.5 to 70.5, 70.5 to 72.5, and then 72.5 to 74.5. That. So those are all the real limits. Again, they're 1/2 a unit above and below the apparent limits, so that we know that everything should go in between those numbers should be in that class. And then the midpoints, because this is just a 2-unit class, the midpoint's really just a point in the middle. So 57 to 58 means that the midpoint's halfway in between, which is, 57.5. This is going to be 59.5, 61.5, 63.5, 65.5, right? It just ends up being the midpoint of each of the classes. 67.5, 69.5, 71.5, and 73.5, like that. Okay. As we'll learn in a little while, these are basically the medians, the midpoints, the medians of each class end up being what we use. Because oftentimes when classes get bigger, get wider, we're going to end up referring to the midpoint when we refer to the classes and do certain things with them. Certain computations will use the midpoint of each class to do so. So that's one of the reasons why we define those midpoints. Questions about all this stuff? Ouch. Now, move on. This, we're getting our data organized in different ways. We're trying to sort of shrink it up and make some sense out of it. This is still like not very, welcoming to most people, right? Still too many numbers, still too much. So let's see if we can figure out our way around that. Let's actually get rid of these numbers and make it pretty. I mean, to be honest, oftentimes it's going to depend, like you wouldn't do both, you would likely do one or the other. It's going to depend on the kind of data you have, whether it's continuous or something like ordinal. And it's also going to depend on how many you have. Like for instance, we only have 43 numbers. In reality, if I was trying to understand 43 numbers, I probably wouldn't go into a group distribution at all. It's not really worth it. Right, we're not really gaining a whole lot by going from one value per frequency to 2. You know what I mean? It's not really doing a whole lot. So I probably would just stick to the ungrouped, just look at them individually. The grouping stuff that we're doing now is really, you got to imagine a much bigger data set. So imagine like 4,000 data points that we're trying to summarize down. This makes a lot more sense, especially if it has a pretty wide range of numbers. This may make a lot more sense to go this route than it is to try and do every single one of those values if it has a large range. So it's not about doing one and then do the other. You're going to be doing one or the other, depending on the kind of data you have, the number of scores you're dealing with, and the range. So just to reiterate this idea of like the real versus apparent class limits. So this is a different, unrelated example than what we're talking about. This is just one I have from a textbook, where here are the class intervals go from 20 to 24, and 25 to 29, and then 30 to 34. Okay, so it's 20, 21, 22, 23, 24. So each of these has a 5-unit interval. Now each class covers 5 units. So as you're going through this, anything that's 20 to 24 goes here. Anything that's 25 to 29 go there. It seems like it makes a lot of sense, right? When you start talking about the numbers between this and this, it can get kind of confusing. I'll give you an example. Have you ever had to have like a cable company out to your house or something like that? They always say, oh, they'll be there between 9 and 3 or whatever. It's some long range. And in my mind, I'm always like, all right, well, does that mean they could be there at 9? or is between 9 and 3, does that mean 10 and 2 really? Because it's really, they're just coming in between those numbers, or could they show up at 3 o'clock? Because if they show up at 3 o'clock, that's not really in between 9 and 3. That's like right at, that's at 3, right at the very edge of that limit. So when people talk about these sort of things, like where they have these sort of bookmarks on time, like between this time and this time, or between this and this, sometimes it can be confusing. Are the parts on the end, the bookends of the range, are you including those numbers in it, or are they dividing the time apart? So that's what happens with this sort of real versus apparent, where it looks like the apparent limits to like this first one is 20 to 24. But if I'm doing that, it looks like the numbers that should go in here are the numbers 21, 22, and 23, because those are the numbers that are in between 20 and 24. But in fact, it actually includes the numbers 20 and 24 in there. So it's 20, 21, 22, 23, 24. So really, to include all of those numbers, the real interval, the real class, the limits actually then are outside of those numbers. So if you look at the bottom, like the real limit of 20 to 24 interval is actually a number somewhere in between the upper end of the bottom of this lower class and the bottom of the next highest class, right? So this is the upper stated limit of this class. This is the lower stated limit of this class. To separate people or scores into those two categories, the limit really falls in between the two classes. So this is the sort of real limits between these two classes, somewhere halfway between. In this case, it would be something like 24.5. That's sort of halfway in between the upper apparent or stated limit here of the lower class and the lower stated limit of the higher class. It's really somewhere in between there. So I think it goes here. If the upper stated limit is 29 for this class and the lower stated limit of this class is 30, the real division, the real limit between them is actually a number like 29.5. Okay, and this, because these have an odd number of scores in them, you can think the midpoints are actually pretty easy. This is a number that's sort of really right in the middle. So 22 is the midpoint of this class, 27 is the midpoint of that class, 32 is the midpoint of that class. It's actually fairly easy to find the midpoints when they have an odd number in each interval. Okay, questions about that? It can often be a confusing topic about the sort of real versus apparent limit stuff. Hearing no questions, I'm going to move on to the next slide. So, if we wanted to be able to take large numbers of data, like again, we got thousands of scores or something, and we want to make some sense of them and actually create a graphic display of them. One of these you see a lot is a histogram. Histograms, you see them all over the place. They're fairly common. I have a picture of one. Maybe I don't. They're a fairly common occurrence. See histograms stuff all over the place. But what are they? So a histogram and a bar graph, people oftentimes will confuse them, and quite often, to be honest, because they're both dealing with sort of bars and sort of quantities of things. It's fairly easy to mistake one for the other, but there's actually very distinct differences between them and sort of how you can tell them apart. So for quantitative data, something like we're talking about with heights, right? So heights in inches. What you really want is a histogram, because a histogram is a graph that displays continuous quantitative data, and it does so by creating a group distribution, which is what we just did a second ago. Right? It creates a grouped frequency distribution, and then graphs that grouped distribution. And that's basically what a histogram is a graph of a grouped frequency distribution, where a bar graph and pie charts, so it's something you can actually graph as either a bar graph or a pie chart. Like if you're graphing something like, oh, maybe I should do this as a pie chart. If you can do that, then it's not going to be a histogram. It's going to be something like a bar graph. So hold that thought for a second. We'll come back to that in just a minute. Let's talk about how do we get a histogram. So for histogram, we're going to take those limits that we created a second ago, which I think we started with 57, and we went up from there, I think. I mean, look back at my picture here, because it's the reason why I took the picture, because I knew we'd be moving on. So, of course, I think I took the picture of the wrong part of it. So I'm pretty sure it went 57, 58, 58, 59. Let's go back and check that for a second. For the lowest number is 57, so 57, 58. Yeah, okay. Just making sure. So down here I can recreate those classes by saying, okay, this is 57 to 58, right? And the next one's 59 to 60. The next one's 61 to 62. 63 to 64. 65 to 66. All right, 67 to 68. 69 to 70, 71 to 72, and then 73 to 74. Okay, so those are the classes that we came up with. And then in each of those classes, we had put together the frequency for each one. So I'm looking back at my phone. The first one, let me step out of the way here. The first one only had 1 in it. All right, just 1. So there's my first one. The second one had 2. And the next one had 4. Sorry about the squeaky marker noise. Next one had 9. 1, 2, 4, 9. So I gotta go clear up to here. Okay. Okay. And then the next one is just the 8. Going off here. Okay, so there's the next category. Okay. Next one had 6. Just here. Okay. Next one had 2. Next one had 7. Which is up here. Okay. And the last one had 4. Okay. So there's a histogram of the heights, where each of these now is, is a class of heights that are being graphed instead of just the single values. This is different than an ungrouped frequency distribution in the sense that we're graphing classes of scores instead of individual scores. But this is how you make a histogram. You first create the classes, and then you plot out the frequencies of each of the classes and that is your histogram. That's what a histogram is. But it's particularly or specifically, it is a graphical display of the of classes, grouped classes of data, grouped classes of continuously scored data that you're trying to sort of simplify down and make into something a little easier to understand. We still get this idea that it does seem to be two humps, right? There's like you know, different things here, but because of the shift from individual scores to classes, it gets a little bit lost because it looks like we have one you know, one most frequent, and then we have another sort of smaller sort of most frequent, but they're not at the same height as they were when we did it individually. So it loses a little bit of that that sort of blended distribution sort of look to it that we had before, but there is still something to say this is likely, you know, the peak around sort of male heights and likely the peak around sort of female heights, but there may be some blend in between there, but still probably the case. Okay, questions about that? Moving on. So important pieces here concerning histograms. So the height of the bar, where the bar falls on the graph, is meaningful in the sense that, you know, on the side we had frequencies here, right? So this is the frequency. Sometimes it might be a percentage or something that's on the side, but usually the height actually means something relative to the frequency of whatever you're talking about. The width of the bars actually are meaningful as well, because fatter bars represent wider classes of scores and skinnier bars represent narrower intervals around, you know, narrower classes of scores. Right? So the width of the bars actually are meaningful as well. Wider bars mean bigger classes. Smaller bars mean smaller or narrower classes. All right, that's what's being said here. So the height, number of responses in that interval, the width is telling you something about the size of the interval. But here's the part that's actually important to tell the difference between a bar graph and a histogram. If the bars are touching, right, the bars touch one another. That means that it is continuous data that's been grouped into classes, and the reason why they touch is because where they touch, you know, when you go, you know, the next bar here and another bar there, that point in which they're touching, represents the real limit between the classes. This line is what separates you either being in this class here versus that class there. Right? It's actually the sort of dividing line. So it tells you, because the bars are touching, that the data were continuously scored and they were put into classes to sort of reduce the size of the overall data set. But the bars touching is important. So if on a test or quiz or something like that, you ask a question where it shows you a graph and the bars are touching, that gives you a clue that it's a histogram. I mean, I guess it could be an ungrouped frequency distribution, but in reality, that you're going to see histograms a lot more than the ungrouped ones, because the numbers of scores are typically in data sets. But it's very likely, it's a very good clue that it is a histogram. Now, on the other side, you got bar graphs. So bar graphs look similar, but they're different because they're used in a different way. So in the same spring semester, I had asked the students, you know, what was your favorite movie genre? The reason I'm using this data too is because this was a larger class. I think I had somewhere, I mean, it's 43 responses. I think I had like 50 or 60 or something students, which is why I'm sort of using this as opposed, because I think in our class we only have 20, somewhere around 20 students. It wouldn't be the data set wouldn't be as useful. So I'm sort of relying on this 2018 data set. But so I just asked students to fill in what was their favorite kind of movie. Or favorite movie genre: adventure, comedy, thriller, suspense, crime or gangster movies or romantic comedies. There's all kinds of stuff in here. Horror, drama, musical. I think that's most all of them. There's science fiction in there somewhere. Yeah, science fiction. So to try to make sense of this stuff, the first thing you're going to do is, again, put them in some kind of order. How you do that could be alphabetical, could be alphabetical by second letter. It doesn't make a difference how you sort of put them in some kind of order, but you need to order them in some way so that they can actually be made sense of. So we can write, I just happen to put them in alphabetical by first letter. So the first category then would be something like, we'll just call this action. And then the next one is, we'll call it A, D, V for adventure. And then you got comedy, C-O-M. You got, let's call this one C. Let's call this one crime, you know, gangster, CG. Drama. All right, drama there. You got fantasy. That's one I missed before. So we'll call this one like fan for fantasy. You got horror, which is my favorite. We got musical. You got romantic comedy, which is of course, you know, separate from regular comedy. You gotta keep those separate. Just kidding. Science fiction. We'll just call it like science fiction there. You got thriller suspense. We'll call that THR. All right, I think that's all of them. I gotta have one extra for fun or something. Unless I missed one. I think I got them all. So with bar graphs, the other thing I want to make a point of here is that as we're going through it, we look at action. Action's got 3. Okay, so we go up to here, and we very carefully draw, you know, this here to say, all right, here is the number of folks who picked action. We go to adventure. I know there's just one of them, but the thing that's important here is that these bars do not touch to indicate that there are separate categories of data. They're not continuous. These are separate individual categories. They weren't grouped. They weren't put into classes. They're just different things. I can actually change the order of these and it would make no difference, just still give you the same information. For comedy, there's 2, 4, can't even count, see? 2, 4, 6, 8, 10, 11. All right, so comedy, there's 11. We gotta be super careful to make sure that we don't cross over into the other ones. Something like that. There's comedy. Okay. For crime and gangster, there's 4 of them. For drama, there's 2, 4 of those as well. But again, we're having these very separate, distinct columns, bars, that are representing different categories. And I could have put drama first and, you know, horror at the end, or however order I wanted to make it. I can do whatever I want because the order is really meaningless. It's just I put them in alphabetical order. That doesn't really mean anything. It's not a numerical order or anything like they are with a histogram. So for fantasy, there's 1. For horror, there's 2, 4, 6, 8. Let's go up to here. All right. So there's my horror bar. Musical is just one musical lover. The musical lover should make friends with a fantasy lover and the adventure person, just because, you know. Anyway, it doesn't matter. I'm just rambling. All right, so romantic comedy, there's 3. That. Okay. Again, sorry about the squeaky marker noise. Science fiction, there's 2 of those. Okay. And then for thriller, there's 5, which is here. Okay, and there's my bar graph. Again, on the surface, without really looking at the details, bar graphs, histograms look suspiciously like one another. Okay, they can look the same. The difference being, ask yourself, if I can take and change the order of these bars and it wouldn't really affect anything, then it's likely not a histogram, right? It's not going to be a histogram. It's going to be a bar graph. Bar graphs, if on the bottom it's some kind of ordinal thing, where I still can, let's say it's, you know, the orders, I think, like if instead of having everyone pick their favorite, had everyone rank order their favorites. So how many people put acting first, adventure first, comedy first, right? I could have put, you know, some kind of ordinal thing where this many people, and this is the order that, whatever. And it would still be a bar graph. Even if I couldn't change the order around, it still would be a bar graph. Because each one of these represents a separate category. It wasn't something that I had to create classes and sort of group values together. So it's the bar graph. Bar graph, important aspects here are that the bars do not touch, right? Do not let the bars touch. Okay. And the width of each of the bars is meaningless because it doesn't really represent anything. It's just happen to be the size of the bar you chose. It doesn't mean that it's a wider class or anything like it does with a histogram. It just means that it's, you know, it's just the size of the bar that happened to be picked for the graph or something. But it doesn't have any meaning relative to a bigger or large or smaller class of numbers like it does in a histogram. So again, with a bar graph, the bars do not touch, the widths are not meaningful. The only thing that they share is that the height of the bars mean relatively the same thing. It tells you the frequency or the percentage or something. Otherwise, they just look similar on the surface, but really are functioning to do different things. With sort of categorical data, so I just mentioned this, like histograms, the height indicates the frequency, but unlike histograms, the width is meaningless, the bars do not touch. So it's like in a first clue. If you see bars on a graph, they're not touching, likely a bar graph, not a histogram. All right. You can also take most anything you can graph with a bar graph could also be graphed with a pie chart. Because again, these are looking at the different categories. They're putting them into percentages as opposed to looking at the frequencies, but it's giving you the same information. Well, what's the largest category that people liked? You know, so it looks like it's comedy was the largest category, right? And you can sort of see the different colors and which represent the different types of things. So like, I can't really tell what color it is, but horror is, I think this 19% one here, if I'm remembering correctly. I can't really tell. The colors are a little bit off. It looks like a dark red, but it doesn't quite match that perfectly, but I think that's what it is. Anyway, so this is, you know, a pie chart, sort of giving you the same information that you have in the bar graph, just putting into percentages instead of total, frequencies. So once we started doing this already, but once we sort of have data displays out, we actually start to graph them, then we started to describe them. And we had our height data, and we sort of plotted it out. We noticed that there were sort of two peaks. And we said, okay, it looks like maybe there's two modes. So modality has to do with how many peaks are there. So if there's one general peak, then we're talking about a unimodal data set. If there are two peaks, it's bimodal. Once you get beyond two peaks, it's really just, people oftentimes will consider it amodal. It's just like without mode, but you could think of it as multimodal if there are multiple sort of peaks in there. And then we also try to think about whether or not the data is symmetric or skewed. Now, symmetric meaning that it actually has sort of a mirror image of itself. And you have positive skewness, which is oftentimes seen as a floor effect, and negative skewness, which is seen as a ceiling effect. And I'll show you that right now. So symmetric doesn't necessarily mean that it's normal like this. This is a sort of has a unimodal and symmetric, but a data set could be symmetric. This is not quite symmetric, but you can have something like a bimodal distribution, right, that is essentially symmetric. So symmetric doesn't necessarily mean just this. It just means that the left and right-hand sides are mirror images of themselves. So when you're thinking about skewness, people oftentimes get confused about the direction because they're like, oh, my teacher in 140 or my previous class over, they always said right and left skew. Now you're saying positive and negative skew, and it's confusing. Well, it has to do with the way that it's pointing. So like here, this is pointing towards the positive side of a XY like coordinate planes, pointing towards the positive side. So that's why it's called positive skew. It's pointing towards the positive direction. For negative skew, it's pointing in the negative direction, which is why it's called negative. So right skew and positive skew are the same thing. Left skew and negative skew are the same thing. So keep that in mind. And the reason why it gets a little confusing. So the previous slide I said that positive skew is what's called a floor effect. So the reason why that is because the skewness, the smaller frequency, large values, right, that are pulling this tail end this direction, they're different. They sort of seem to be different than where most people are sitting. So the majority of people are in this section on the lower end of the distribution, because they're over here. So where these people are sort of pulling the distribution this way, they're pulling it up because they're unusually large. Most people are sitting at the bottom or sitting on the floor of the distribution. They're on the very low end. They're sitting on the floor of the distribution, so that's what this is considered a floor effect. People are responding mostly on the floor or at the bottom, with few people on the very high end. Same thing in reverse. Most people in a negative skewness, most people are down here. I'm sorry, I shouldn't say that. They're up here on the positive side. They're up on the positive end with a few very large negatively scored negative values on this end, pulling it down. But here, everyone is sitting at the top, which is what's called a ceiling effect. They're sort of sitting at the very top of the distribution, and it's causing them to sort of hit a ceiling and all be piled up there. So sort of piled up on the ceiling versus piled up on the floor. And anyway, you get the idea, I hope. If a distribution has one mode, one highest point, it's considered unimodal. If it has 2 points like this, it's considered bimodal. You can't have trimodals and multimodals and all that kind of stuff. And there's a joke in there about having distribution that's allomodal, but if it doesn't matter. So that'd be actually kind of nice, little distribution, a little ice cream on top. This would be like a sundae. Anyway, so you get the bimodal is usually what you're going to see. As about as much you're going to see. People don't really talk about tri and multi and stuff. It's either it's got 1, 2, or none. Because as soon as you get to multiple modes, the idea of using the mode becomes sort of not useful anymore. And then you got the ever popular, ever famous normal distribution that has sort of 3 requirements: that it is unimodal, right? So one mode, it's symmetric. So that means that the mode is in the middle and has a sort of symmetric look to it. and a nice sort of bell-shaped curve that we're used to with normal distributions. And the last one's a weird one. It's called asymptotic. So down here at the bottom, this line, the very bottom of this, is a sort of zero limit, right? So this is like zero. It's going, in terms of probability or whatever else, it's going towards this sort of 0 point. If you're thinking about it like as a coordinate plane where, this is our sort of y, or let's say this is like probability or something, proportion or whatever. It's sort of working its way back. So the most probable is somewhere in here, right, the highest point, and then it's on each side, it's sort of working its way down to the least probable or least frequent. What asymptotic says is that a true normal distribution, even though it is sort of as scores move away from the center, as you move away from here, scores get less and less likely, right? The probability goes down, the frequencies go down, but it never actually reaches 0. So these continue down theoretically infinitely all the way down. It never actually gets to 0, and that's what makes it asymptotic. It never actually reaches the asymptote, the limit of 0. It just gets smaller and smaller and less likely, but it never theoretically reaches that 0 point. Functionally, the values could be small enough that they're essentially 0, but in theory, it never actually gets to that point. It never really reaches a 0 mark, even though it just gets smaller and smaller and smaller.